Hi, so welcome to Math 310 Modern Algebra. This is lecture 19. And so we're now going to go back to groups. So, it's been a while since we've been directly looking at groups, but we've at least been indirectly looking at them with rings because rings are sets that have two operations and they are a group under one and almost a group under the second. All right, so what I want to do is I want to try to prove some results to help us figure out what types of groups are possible. So we'll be mostly looking at finite groups in this class, but we can look at some other things as well. And if there's time at the end of today, I'll talk a little bit about some of the interesting problems with infinity. So the first question is, what size groups are possible? Is there a group of size n for all n greater than or equal to 1? What do you think? Is there always going to be a group? And you always find a group of size 1, 2, 3, 4. If I give you any positive integer, will there be such a group? Yes, okay. Why? So one is you can give me this elaborate abstract proof, or you could physically construct a group of size n.
I was gonna say like mod n.
Okay, so look at integers mod n under clock laws. So we know that there at least has to be one group of size n for any n. Another way of doing this, equivalently, let zeta sub n be e to the 2 pi I over n. And you can look at the cyclic group e zeta n squared dot 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 zeta n to the n minus 1 under multiplication. And actually, I guess rather than writing e, I should probably write this as 1. They're basically equivalent because we're just adding the exponents. And if I take the nth root of unity and I raise it to the nth power, I'll just get back 1. Okay. Now the next question is, for what n are there two groups? Any thoughts about what the smallest n might be? And you want to eliminate. What about n equals 1? You could have more than one group of size 1. So you would have to have two different groups. And again, by different groups, I can't just be calling them different names. So the question is, are these two groups here the same group? Just written differently. One I've written additively, one I've written multiplicatively. There's a nice map between them. You give me the integer 5, and I will map it to zeta of n to the 5th power. You give me 7, I'll map it to zeta of n to the 7th power. These two groups are really equivalent, because the way I multiply two numbers is I add their exponents mod n. So these are actually equivalent. So even though they look different, one is written multiplicatively, one is written additively, these are really the same group. So I'm not going to count it as I found two different groups of order n. Okay. What about a group of size 1? Do you think you could have two different groups of size 1? So what element does every group have to contain? The identity. If your group is of size 1, can you have anything other than the identity? No. So, oops, getting closer. So, only possibility is just the set containing the identity. So when we take n equals 1, we're not going to be able to find two distinct groups. What about n equals 2? We know we have to have the identity. And then we have some other element x. What can you tell me about x? X needs to be the inverse of itself. Good. What else? I want the group to have two elements. So what must be true about x? Has order 2. What else? You're close. Well, tell me what x is not. X can't be the identity. So here we have x is not the identity. X equals x inverse. So it's completely forced on me. I have no choice. What about n equals 3? Now things are getting a little bit more interesting. I have 3 elements, e, x, and y. And we can start trying to think of what are the different possibilities. So I have to decide what is x times y, what is y times x. So what are x squared, x cubed, x to the 4th, dot, 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 y squared, y cubed, y to the 4th, dot, 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 xy, yx. What can you tell me about x squared y? What are the possibilities that x squared y could equal? We have n equals 3. We have the group G is E, X, and Y, with all 3 distinct. What does x squared have to be? What are the possibilities? E or y. Here is one of the possibilities. Right, so x squared equals E, X, or Y. Those are the only possibilities. You eliminated x squared equals x. If x squared equals x, then x inverse x squared equals x inverse x, or x equals E contradicts. So we know that x squared is not going to be x. It's either going to be E or Y. Could x squared equal E if the size of G equals 3? What do you think? Any thoughts on what theorem we might be able to use to try to get a sense of whether or not this is possible? Haven't used this theorem in a long time. Yes. Excellent. The order of an element has to divide the order of a group, or the order of a subgroup has to divide the size of the group. What do we know about the size of the group? It's 3. So if x squared equals E, then E x is a subgroup of order 2, but 2 does not divide 3. contradiction by Lagrange. Therefore, what's the only possibility for x squared? Why? I have no choice. If I'm looking at a group of order 3, this is the only thing that's possible. It's cyclic. Do you think every group is cyclic and that for every n there's only one possibility? Or have we not gone far enough in n? So we've definitely shown you give me any n, I can always give you a cyclic group. The question is, what other groups are possible and how does that depend on n? So far we've analyzed n equals 1, 2, and 3. Anything special about these numbers? Yeah. All of them? 2 and 3 are prime, and 1 is just the unit. So maybe our argument generalizes, maybe conjecture. If n is prime, only one group. Does that seem a reasonable conjecture? Yeah. Can we somehow take what we did a few moments ago where we used Lagrange? And the issue we had was, x squared couldn't be the identity because then we would have a subgroup of order 2, and 2 doesn't divide 3. So if we have n is prime, so say n equals p is prime, we can look at the group x, e, say x2, x3, dot, 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 x. And so we can just keep forming higher and higher powers of the second element in our set. We know by Lagrange, K has to divide P for P is prime. What's the only possibility for K? Well, what are the only possibilities? There's 2 possibilities.
One and itself.
One in itself. So K is either 1 or P. If K equals 1, then x2 equals E, which we are assuming x2 does not equal E. Therefore, K equals P, the order of x2 equals P, so the group G is just going to be E x2, x2 squared, dot, 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 x2 to the P minus 1. Only one choice. So if I give you a group of prime order, of prime size, there's only one choice. So what should be the first n we should investigate? Where we have a chance of seeing something other than a cyclic group. 4. N equals 4. Does anybody remember a different group of size 4 that's not the same as this one? We've seen this many times. This is one of our go-to examples. Any thoughts? The whole group mod 12?
The relative prime.
The relative prime. So if you look at, Z mod 12Z, the multiplicative group, that's going to be 1, 5, 7, and 11. All elements. So we have finally found an n where we have two different possibilities. And then the question becomes, as we keep increasing n, how many possibilities do we have? And which ones are realized? And so one of the things I want to talk about is the difference between necessary and sufficient. So this is something that is often missed by people early in their math careers, confusing a necessary condition with a sufficient condition. Can somebody tell me the difference between necessary and sufficient? So what's the difference between necessary and sufficient? If you can't tell me the difference between necessary and sufficient, can somebody define either necessary or sufficient?
I can do it in English.
Okay, that's fine.
Necessary isn't required.
Okay, so necessary is required. And what's sufficient?
Sufficient, good enough.
Okay.
I don't know how you would break that down into 4 foundation. I use the language.
So if any baseball fans here? Can somebody give me a necessary condition to win the World Series? Yes. You have to have a baseball team. Can you give me a stronger necessary condition? Not necessarily. You can get very, very lucky. So if you want to win the World Series, you should. Okay. No. That's not. I want a weak necessary condition. Hold that for a moment. A weak necessary condition. So it's not just enough to be a baseball team. Any Buffalo Bills fans here? Buffalo Bills are famous for this. What is a necessary condition to win the Super Bowl? Yes. Get to the Super Bowl. And so the Buffalo Bills did that 4 years in a row. And what happens after you win the Super Bowl or the World Series? They give you a shirt that says champion immediately. Do you think they make those shirts on the spot? No. They have to make up shirts for both teams. So the joke is, and I think this is true, what do you do with all the shirts that say Super Bowl champions for the team that just lost? And so I've heard they send them all over the world to poor people. And I'm just imagining this village with this poor kid. Mommy, they did it 4 in a row. Go Bills. So anybody who is a Bills fan knows that just making the Super Bowl is not sufficient to win. It's necessary. You can't win the Super Bowl without being in the Super Bowl. Now let's go to your comment. What is a sufficient condition to win? Score more than the others. So as long as you score more than the others, you will win. Okay, there's a big difference between necessary and sufficient. Just because something is necessary, just saying that it's been checked off, that it's been done, is not enough to ensure that you have the result that you want. For example, I will risk going back to analysis. Let's say we have a sequence of terms an, and we want to study the sum of an goes from 1 to infinity. You should have all seen formulas for stuff like this, maybe in Calc 3, sequences and series. Can somebody give me the necessary condition for the sum to converge? For a sum to converge, it's necessary that what the about is.
Some.
Well, AN is the terms in your sum. What must be true about the individual terms in your sum if you want the sum to converge? What do they have to be going to? So if you want this sum to be converging to a finite number, if the ANs are going to infinity, is that going to converge to a finite number? No, it's going to explode. So if you want that sum to converge to a fixed number, what must be true about the individual pieces that you're adding? They get smaller. In fact, they get closer to what? 0. I could say, for instance, AN equals AN minus 1 plus, no. You just said getting smaller. So maybe my first term is 1, my next term is 0.999999, the next term is 0.999998, then 0.9999, and they're getting smaller, but there's still always a good boost. And so if I want the sum to converge, I want the terms to be going to 0. It's not enough that they're just getting smaller, they have to be going to 0. The other thing is you have to be very careful about English versus math. Is -2 smaller than 1? Yeah, it's less. So you might want to say smaller in magnitude. So if I just had the terms becoming smaller, well, if they became incredibly negative, they're getting smaller and the thing is going to go up to minus infinity. So is it sufficient? Is this a sufficient condition? No. I believe we did this series early in the class. Does anybody remember series? Come on. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and that diverges to infinity. So this is a great example of the difference between a necessary and a sufficient condition. Now, you can try to figure out what is the weakest sufficient condition you need for a sum to converge. And you might remember the rational, the root test, the ratio test, the comparison test, all those various things. So, a sufficient condition. Let's do the ratio test. If the limit as n goes to infinity of AN plus 1 over AN in absolute value equals rho is less than 1, then the sum converges. Does this seem vaguely familiar? Okay, I'm not going to prove it. If anybody's interested, I'm happy to prove it. This is a sufficient condition for convergence. You might still be able to converge even if this is not true. For example, if we let AN equal 1 over n squared, then 1 plus 1/4 plus 1/9 plus 1/16 plus dot, dot, dot converges, but rho equals 1. And yes?
So you're saying sufficient is like you have a condition, but you don't necessarily need the condition.
Right, this is enough. A sufficient condition to pass this class is for $1 billion to arise in my bank account tomorrow. That is not the only way to pass this class.
For the Super Bowl example, you said a sufficient condition is to score more in a Super Bowl.
Correct, and
why is that not necessary? Because you can't win.
so sufficient conditions can also be necessary conditions, right? So a sufficient condition could also be necessary. So scoring more points is sufficient, it's also necessary. In a situation like this, it is sufficient for the ratio to be less than 1, but it's not necessary. I can give you a sequence 1 over n squared. And when you do the ratio test, they should have told you if rho is less than 1, it converges. If rho is greater than 1, it diverges. If rho equals 1, you have no information. And if it's going to be an exam, almost surely you'll have at least one problem where rho equals 1. But this is a subtle point that I have found a lot of people get confused over the years. And given that several of you are going to be educators and teaching classes, really wanted to drive home the difference between what is a necessary condition and what is a sufficient condition. Sometimes sufficient conditions are necessary. But sometimes there's other paths, and sometimes there's more than one way to get where you want to go. Yes?
So a necessary condition is the thing you're trying to prove implies this condition. A sufficient condition is the condition implies the thing you're trying to
Let me make sure I unpause as well. So we're trying to prove something.
Yeah.
If you show that a necessary condition does not hold, then there's no way that what you're trying to prove can work.
Okay.
It's a minimum ante.
Okay.
You know, I need this necessary condition to get in the game, but it's not necessarily enough to win. A sufficient condition is enough to win. There's frequently more than one way to win. And so in something like this, when I'm trying to determine which sums converge, you know, the ratio test, the root test, these are all great, but I can give you examples where these tests provide no information. And so, you know, it's not required that the ratio is less than 1. It's easier if that's the case. Okay, is everybody comfortable with the difference between necessary and sufficient? Okay, so now, oops. Okay. Does it always have that extra space on the sides, or? It just seems like it's somehow compressed page a little bit. There we go. Okay, yeah, it was compressing it somehow. Okay. So you should have thought about the checkerboard problem. And so what I'm doing is I'm going to give you a checkerboard. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. And what I'm doing is I'm going to remove the bottom left and the top right squares. I'm going to give you a bunch of 1x2 tiles. And the question is it possible to cover the checkerboard using just 1x2 tiles?
You can't rotate it into a 2x1 or?
You can vote 2x1, absolutely. You can spin it however you want. You just can't put a tile on top of another tile. You can't have a tile overhanging across the board. There's a lot of ways to stop putting things down. What should you be looking at rather than this problem? Yeah, start off with a 2x2. So if we start off with a 2x2, what do you think with a 2x2? No. What next? 3x3. I claim we don't have to worry about the 3x3. Why don't we have to worry about 3x3? Odd number. So if n by n with n odd have an odd number of spots, each tile takes an even number. So we know there's no way to do it on a 3x3. There's no way to do it on a 5x5. We now have a necessary condition. If I want to be able to cover things with 2x1 tiles, then the board size has to be even. So I don't even have to consider 3x3. I could start looking at now a 4x4. So 1, 2, 3, 1, 2, 3. And now there's a lot of ways to put things down. By symmetry, I know I would have to cover maybe this square either goes up, or if it doesn't go up, it has to go sideways. So I would have two cases to consider. Let's say we do the sideways case. And so what I'll do is I'll make a copy of the board. So we'll take the first 2 by 2, and we'll go this way. As soon as we do that, we know something about what's underneath it. What has to happen to that square that's underneath it in the bottom row? How does that tile have to be oriented? On the side. And then what about the one now in the bottom right corner? That has to go up. Right? And then the one above that has to go to the left. And very quickly we see it can't be done. The other possibility was I could have gone up. Well, if I go up, then I know the upper left corner has to go to the right. And then the one on the right has to come down. Then that one would have to come down. That would have to come over. This would have to come up. And again, we have a problem. So impossible. So this wasn't too bad looking at 4 by 4 boards with the 2 corners missing. You could try to do that now with this board, which is a bit longer. And there's more possibilities. And the more possibilities you have, the more painful, the harder it's going to be. Does anybody see a good way to prove that it's impossible on the larger board? Yes.
So for this, you would have to assume that these have colors.
You don't have to assume, but you can put colors on if you want.
For this specifically,
Okay.
I think I heard of this.
Okay.
Doing this, you could show, I don't know how you would show this, but it will hold that if you're taking a square from the top right and bottom left, those will be of the same color.
Mm-hmm.
So let's assume they're white. So you're going to have n black tiles and n-2. When you place one of those 2 by 1 squares on the board, you're going to remove 1 black and 1 white.
Good.
And that will leave you with I think 2 blacks remaining and 0 whites.
So good. So every time we put on a tile, the tile is always going to cover 1 black and 1 white. So we start off with, let's do 8 by 8 board. There's 64 tiles, so there's 36 of each initially. We've removed the 2 white tiles in the corner, so it's going to be 36, 34.
I think it's 32, 30.
Oh, sorry, 32. Sorry, thank you. 32, 34. No, sorry, 32, 30. Sorry, 32, 30. So we have 32 black tiles, 30 white tiles because we removed 2 white tiles. And every time we put down a tile, we have to remove 1 white and 1 black. So after one move, we're going to go down to 31, 29. Then 30, 28. And eventually, we get down to 2, 0. So it's impossible. This is a great proof, and it's a concept we've seen many times before. Does anybody remember the word that describes this? We saw this with the 100 hat problem recently. Nope. Something that begins with P. Parity. It's a parity argument. Basically looking at things almost mod 2. Absolutely wonderful. So we don't have to go through all the different ways of putting things down. It's enough to just argue like this, and we can immediately see there's no way to do it. Why was there no way to do it? Because we removed two squares of the same parity. So what do we do? Page. So what if we remove one black and one white? Do you think it's doable now? So let's start off with a 4x4 board. So I'll put in some numbers, 1, 2, 3, 4, 1, 2, 3, 4. Somebody give me two squares to remove, or at least one square to remove. Top left. So we will remove the top left. Now I want someone else to give me a different square that's not the same parity. So it can't be on the same diagonal. If it's in the top row, it can't be the third element. If it's on the left column, it can't be the second element. So somebody give me another square to remove. The right. So that would make things really easy. Thank you. Right. This is going to be now very easy to tile. I can just go boom, 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 boom. So in that case, it's not going to be a problem at all. Okay. Let's do another one. So we'll keep the upper left corner. What's another one I could remove? Yes. 3 from the left and 1 down over here. So that is not the same parity. And so if I try to just go through this, see boom, 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 boom. So I was able to get that without any trouble. So we know a necessary condition is if I remove, I have to move two of different parity. Is that sufficient? So, can you always tile with 2 by 1 if you remove any two squares of opposite parity on a n by n board where n is even? So I'll leave this for you to think about, but this is how you get into a research problem. You start off with something simple, something that you know, a problem that you might have seen before, and you start asking questions. And if yes, how many ways? Do certain removals give you more possibilities in terms of how you can fix things? I just got started for a second because the clock was actually working. It's not right, but it's at least working. So I think you might just be missing the daylight savings adjustment. Okay. So these are two of the most common questions you ask in mathematics. Can it be done? And if the answer is yes, how many ways can it be done? So we could make the problem a little bit more interesting. What if we remove 4 tiles? What do you think if we remove 4 tiles? What must be true? Well, it could be a configuration so it's not gonna work.
Is the goal to place the 2x1 tiles on all remaining tiles?
Yes.
Okay.
So can you give me 4 tiles to remove, 2 white and 2 black, so that I will not be able to tile things? Any thoughts? Or do you think it's always going to be possible, no matter what I remove, I've removed an even number, the same number of whites and blacks?
Everything's except the top of left corner, but all around it.
Yeah. So yeah, with numbers it's easy. Okay, 3, 1. Okay. And what else?
3, 2,
Going up. Good. And what else?
4, 2,
Good. And
3, 2, 1.
on 2, 1. Okay. I wasn't sure if you're going to do 2, 1, or if you're going to do 4, 3. Either way works. So by doing it like this, you've trapped, and there's no way to do it. So it's not always possible. So it is necessary, but not sufficient, to have removed same number of each color. Don't know yet if it's sufficient when we remove just 2 tiles, 1 of each. It might be the case. So I'll leave that as something for you to explore and play with. Is it sufficient? Can you always do it? It may be a challenging proof, and as the board gets larger and larger and larger. For problems like this, it can become extremely difficult to investigate. If I give you a very large board, then without loss of generality, you might as well remove the first one in, say, some triangular region like this, because by symmetry, by flipping the board, by rotating, you can always assume the first removed piece is somewhere in there, and that's going to make the problem a lot easier to look at. So these are some things to think about. For us, we're trying to think what groups are possible. If I tell you how many elements I want the group to have, can I find a group with that many elements? And the answer is yes. We have the trivial cyclic group. Okay, is there something that's not cyclic? And then how do the number of possible groups, actually the realized groups, how does the number of groups for given n depend on n? What property of n do you think might play a role? From the limited data we've seen. I'm sorry? Being prime, or more generally, the factorization of n. So depending on how n factors, that's going to have probably a big impact on what groups are possible. So what a lot of the chapter 6 does now is it tries to develop techniques to help us analyze structures of groups. And a lot of times we know how many elements something has. And frequently that allows us to narrow down the possibilities. If there's more than one possibility, then you have to do more work. If I tell you I have a group with 4 elements, we know that there are 2 possibilities at a minimum. Could there be more than 2? So let's say n equals 4. We could have the group, 1 x squared, x cubed, where x to the 4th equals e. We also had the group 1 x, y, z, where x squared equals y squared equals z squared equals e. And what is xy equal? You should be able to figure it out even without looking at what we've done before with the 1, 5, 7, and 11. What's the only thing xy could equal? Has to be, I'm sorry? So if xy equals e, then y is x inverse, but x equals x inverse, so y would have to be x. And we want the three elements to be distinct. So we know xy can't be e. So xy can't be e, and xy can't be x, else y equals e, and xy can't be y, else x equals e. So what's the only possibility for xy? Z. And in fact, what does yx have to equal? Also equals z. And then similarly, you would get xz equals y equals zx, and you would get yz equals x equals zy. So what kind of group is this? So what can you tell me? What kind of group would this be? Abelian. So this would have to be abelian. So there's at least two possible groups of size 4. They're both abelian. Could there be another group of size 4? No. Is there another group? If yes, must it be abelian? So let's try to think. Say equals 4, and we have e x. If x squared is not the identity, well, could x squared be the identity? Is that possible? I give you a group of order 4. Could I have an element of order 2?
Yes.
Yes. So, case 1, x squared equals e. Case 2, could x cubed equal e? As the smallest time that we get the identity. So this is no by Lagrange. Could x to the 4th be e? Yes, well, so we're in the situation where x squared equals e. So we have to have a what must be the order of y? Y can't be the identity. Y is not x. Y is a new element. By Lagrange, what must be true about the order of y? 4 or what else? Or 2. Could y be an element of order 4? Order of y is either 2 or 4. So if the order of y equals 4, then the group is just e, y, y squared, y cubed. And what would x have to be? If x has order 2, x would have to be y. So you got to be very careful not to throw things away. it is possible that y has order 4. That would not contradict anything we've seen. It just means that when we chose the element x, we chose an element that was the square of something in the group.
It's not distinct.
I'm sorry?
Would it still be distinct, like the x and the, since x equals to y squared?
Right, x and y would still be different elements. Right? So x is y squared, so x is not y. So there would be two distinct elements. And so in that case, x is really just y squared, and then the last element we would have to add would be the y cubed. We've already done this case. This is the cyclic case. So the only thing left is now we have to assume the order of y equals 2. So we have something in the form e, x, y, and one other element with x squared equals the identity equals y squared, x and y are unequal. What's the only possibility for that remaining element? Because we want it to be a group, so what has to go there? So what are the properties a group has? The group has to have 4 properties. It has to have an identity, has to be associative. What else? Has to have an inverse. What else? Closed. So what's the only possibility for that last spot? If it's going to be closed, what do I have to put here? There's only one choice. Well, actually 2 choices, and they have to be the same. What has to go there? It's got to be closed. So if it's closed, it means no matter what 2 elements you take in the group, if you multiply them, it's got to be in the group. If I take x times x, that's x squared, that's the identity. We already have that. If I take y times y, that's y squared, that's the identity. We already have that. What's the multiplication we haven't done? X times y, or y times x. So we have to have xy equals yx. That has to be the missing element. We have no choice. And since xy equals yx, what does that give us? Well, if I look at xy times xy, that's the same as xy times yx, right? Which is x, y times x, because I can regroup things. What's y squared? E. So this is, x, e, x, which is x squared, which is the identity. So we have a third element of order 2. We've actually just rediscovered the group we had before, because we said before that z had to be xy. This is 1, 5, 7, 11 from before. We're just using different language for it. So there's only 2 possibilities if I give you a group of size 4. We saw earlier when there was a group of prime order, there was only 1 possibility. Do you think if I give you a group of prime squared order, there's only 2? Or do you think maybe something is special about the prime 2? Not enough data, right? What should we do? Gather more data, right? When in doubt, gather more data. What prime should we look at next? 5? So we just did 4. And if I'm trying to see if there's only 2 choices, if I have a group of size prime squared, what would be the next natural thing to try? 9. So you could try as an exercise, find all groups of order 9. You know there has to be, every element has to have order either 3 or 9. As soon as you have an element of order 9, the whole group is cyclic. So you start getting elements of order 3. So you can start playing these games. So, right, n equals 9. If there exists an x in G with the order of x equals 9, then G is 6. So all elements that are not 1, I guess that's because they're not E, have what order? So if we have one element of order 9, then the group is cyclic. So we might as well assume we don't have anything of order 9. So what must be true about the order of everything else? What do their orders have to be? 3 or 9. But we're going to assume that we don't have any elements of order 9. Because if we have an element of order 9, we know what to do. So we know it's cyclic if there exists an element of order 9. So assume no element has order 9. Because we can handle that case. So let's assume that there's no element of order 9, because if there's an element of order 9, the group has to be cyclic. So what's the only possibility left for all other elements other than the identity? What does the order have to be? Has to be 3. And so now let's start trying to figure things out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we put in some element. We have an element x. The order of x has to be 3. So we also get to put in x squared. And then x cubed would just be the identity element. So that's it. We now put in a new element. What should we call the new element? Y. It needs a name. Bad joke. Out of curiosity, how many people know the who's on first routine? Okay, just curious. And we know we have y squared. What else do we have to put in? We have to put in xy. What else do we have to put in? We have to put in x. So that's a great thing. X squared, y squared. Is x squared, y squared different than everything on the list? Wait, did you say x squared, y, or x squared, y squared?
X squared, y squared. Like,
Oh, the square of that element?
well, yeah, both of them squared. So multiplying squared.
Okay. So the question is, could x squared, y squared be something already on the list? We have a lot of multiplications that we now have to do. And so we have to have xy times itself. So could xy squared equal something we already have? What about x squared y equal something already have? What about yx equal something already have? Maybe yx is the same as xy. There's fortunately not that many possibilities. And you could say, let's assume xy squared is something already on the list. Does that get a contradiction? Or is the square of that something new? So let's say xy equals x. Then you would get yxy is the identity. Right? So if xy squared equals x, then you get yxy equals the identity. What's that the same as? X equals the identity. Good. How did you get that? Good. So I could multiply the left and the right by y, and y squared is the identity. So we would get yx, y equals y x equals e contradiction. So we've just shown xy squared can't be x. 1 down, 3 to go. Right? And then things might start getting harder and harder. Could xy equal x squared? Well, if I multiply on the left by x squared, I would get yxy equals x. And if I multiply on the right by y, since, oh, wait a minute. We don't know that y squared is the identity. Y is of order 3. So we have to go back in time a little bit. So we don't multiply by y. What do we multiply by? Y squared. So we get y cubed x y cubed equals y squared e y squared. So x would be the same as y to the 4th. X equals y contradiction. We still get a contradiction, but a slightly different one. If we tried xy equals x squared, we would get yxy equals x by just multiplying on the left by x inverse. Now we could multiply through by y squared on the left. We get xy equals y squared x. So that's a possibility. And I could get maybe xy x inverse equals y squared, some kind of conjugation. The point is, it's getting harder. How many of you remember, Green-Gauss-Stokes theorem for multivariable calculus? The whole point of how many of you, at least, were in a class where they mentioned those? Okay, and the whole point is, rather than doing some very painful line integrals, you can convert it to a nice integral frequency. Especially if you're in a situation where the curl is 0, then you're just integrating 0, which is very easy to do. And so this is why you develop some advanced machinery. I'm no longer having fun. Okay, for a while I was having fun. It was kind of cathartic to do it and whatnot and do these calculations. But you start to see the number of possibilities is just growing rapidly. And this is when the prime is 3. Right? It's going to get much worse the further you go. And you have to look at all the different possibilities. You could write a computer to try to go through and create multiplication tables and figure out what is possible. But the number of things that xy squared could equal now is so many. It's getting harder and harder. If you make the assumption that the group is abelian, then it becomes a lot easier. Because then we would know xy would have to be the same as y squared. We could move things around a little bit. And there is a theorem in the book that says that if the group has order prime squared, then the group is abelian. And you can begin to see now why we would want something like this. So sadly, one of the best ways to appreciate theorems is to suffer not having them. And when you suffer and you do the calculations and you see how painful it is, then you appreciate the power of the theorem and why you try to generalize and why you try to prove these results. So hopefully the exploration of possible groups, which we will definitely stop at this point by doing by hand, will give you an appreciation for the theorems we're about to prove, which is going to really cut down on the possibilities. Okay, so now we need to shift gears and we're going to talk about groups acting on sets. So definition 6.13, so G is going to be a group and X is going to be a set. So the action of a group G on a set X is as follows. We have to come up with some rule so that if you give me an element of the group G and you give me an element of the set X, then I can associate something in the set X. And I'm going to call that G dot X. So G sends X to some new element. And I want the following two items to hold. And if you think about it, these are two extremely reasonable things. I want the identity axiom. If I choose my group element to be the identity, then what element of X do I get back out? Whatever I started with. It doesn't change things. The identity element's impact should be to leave you alone. That seems very reasonable. The next is associativity. We love associativity. If I first apply G2 and then I apply G1, that should be the same as applying the element G1, G2. Okay, is everybody comfortable with the definition of what it means for a group to act on a set? I have to give you some rule so that if you give me some element in X, you give me some element G in the group, I can associate a new element in the set. So whenever you see a definition, you should always be trying to ask yourself, can I come up with an example? All right, so this is the definition. Is there any set and any group where the group acts on the set? So there's one obvious example where if I give you a group, there's always a set you could take. I think that would work because it says for each element in the set, and there are no elements in the set. So I think it works, but let's come up with a non-empty X. So if I give you G, can always take X to be what? For given group G, there's always a set that G can act on. As soon as you see it, you'll kick yourself. So you could take X to just be a one element set and define the rule, I send everything to itself. So you could just take it to be basically you could just take it to be something trivial. That would work. There's another thing you could choose for X that will always work. It's going to depend on G. But there's another thing you could take X to be where you know you can define something. So if I give you any group, there's always a set that group can act on. You get to choose that set, and that set can depend on G. What's the simplest thing you can think of that depends on G? G. I could have the group act on itself. Right? You can always have the group act on itself. Will that work? Yes. If I take the identity and X is in G, then the identity times X is just X. And if X, G1 and G2 are all in G, associativity holds. I can always have my group act on itself. So there will always be a choice of X that will work. Frequently, there will be more than one choice of X that works. And this is where things get hard. When I want to analyze things, I have to figure out what is the right X to look at. I know, of course, everybody has already finished reading chapter 6, so I apologize for talking about things that I know you have already read and mastered. But in the proof of the first Silo theorem, you have this wonderful step where they decide to look at all subsets of size p to the n. And that was the inspiration in the proof, is that's a good set of things to look at. This is where things can get very challenging, trying to figure out what do I want to try to apply these ideas to. Okay. What class should you have taken before this? Linear algebra. Can you see a way to use this in linear algebra? What would your set be? What would your group be? Can we? What would X be? If you're doing linear algebra, what do you want your items to be? What are the main things you would study in linear algebra? Matrices, what else? Vectors. So which do you want to be X, the matrices or the vectors? So X is what's going to be acted on. Should that be the matrix or should that be the vector? So you would want, so what would then be acting on the matrices? So is that what we normally do? We normally take a matrix and apply a vector to it? We normally go the other way. We take a vector and apply a matrix to it. We have AV or AX. So X would be vectors. And G would be some group. And then the question is, what group could we do? We could do maybe translations, maybe rotations. We can't do an arbitrary matrix because we have to be careful because not every matrix is going to be invertible. We have to make sure we have a group. So if you remember your orthogonal matrices, these are the set of all Q such that Q transpose is Q transpose Q is the identity. That's going to be a group. And if you think about it, you know, if I rotate by 40 degrees, then I rotate by 30 degrees, that's the same as rotating by 70 degrees. So things are going to work out nicely there. Well, if I want to do translations, if I shift by a fixed vector, and then I shift by another fixed vector, that's the same as just shifting by their sum. We've seen this when we did the Caesar cipher. If I shift every letter by 3, and then I shift every letter by 8, that's the same as shifting every letter by 11. So we've seen stuff like this before. The problem is, if I look at the space of all matrices, not all matrices are invertible, and that's not going to give me a group. Hopefully you've seen something like, you know, GLN of R. This would be the set of all n by n invertible matrices with real entries. Have you seen this notation? GL for general linear. Okay, so this would be a group of matrices. I can't do GLN of Z, you know, n by n matrices with real entries that are also integers, because when I take inverses, I might not stay in the integers. But I could put in the rational numbers, because the inverse would be a rational number still. So this is at least something that we have seen before. When you've done linear algebra, we can actually interpret this in that setting. In terms of, you know, the big theorem I mentioned that we're not unfortunately going to be able to get to this semester, that if I give you a polynomial of degree 5 or higher, you can't write down explicitly the roots in terms of the coefficients. That does involve, you know, having certain groups acting on the roots. And there your set X will be the roots of the polynomial, and the group will be the permutation group. You just, which roots can you interchange? Okay. Okay. So now we take some set X, we choose some element little x, and we have the group G act on little x. And we can look and see what are all the different values that come out. And we'll collect them all together, and we're going to call that the orbit. So the orbit of x is we fix our little x here, and we multiply on the left by every element of the group. And we put them all together, and that's the orbit of x. And then if I change my x to something else, to x prime or x tilde, I would get a different orbit. And so for each element, I can look at its orbit. And there's a lot of questions you can ask. One is, are there any elements of G that leave x unchanged? That when I apply them, I come back to where I started. And we will call that set the stabilizer, or the stabilizer of x, and we denote it as G sub x. And this is one of the main reasons why I wanted to paste this from the book. Because if you have bad handwriting, one of them is G followed by a regularly sized x, that's the orbit. The other is G followed by a subscript x, that's the stabilizer. If your handwriting is bad, it can be very easy to confuse the two. The subscript is telling us these are all the elements of G that leave x alone. When it's a regular sized x following it, it's the orbit of x. It's what we get is we keep applying elements of G again and again and again. Sometimes, how many of you have done probability? So if you have a random variable x, they sometimes write the random variable like this to distinguish a capital X from a lowercase x. Because it can be very easy with bad handwriting to confuse the two. Sometimes books use they use boldface for things. Like they might use boldface R to denote the real numbers. You saw how long it took me to write that. You're not going to do that in a lecture. So rather than do that, people often write the real numbers like this. As just a faster way of doing boldface, which you can't do on the board. Okay. So where does G sub x live? So where does G sub x live? It's a subset of what? G. G sub x is a subset of G. So it's natural to ask, is it a subgroup? It lives inside a group. Is it a subgroup? That's one of the first things you would ask. And the answer is yes, it is a subgroup. And so proposition 6.19, if G is a group that acts on a set X, then we have three items. So I'm going to just list the first two here. The first is the stabilizer is a subgroup of G. The next is we have an equivalence relation. We say X is equivalent to Y if Y is X for some G and G. That means they're going to be in the same order. Between the All right, so we're resuming the recording. Technical difficulties have hopefully been fixed. And then the last part of the theorem is that there is a bijection. If we look at G mod G sub x, the stabilizer, there's a map from that to the orbits. And it turns out that the number of elements in the orbit is equal to the ratio of the number of elements in G to the number of elements of the stabilizer. This is going to become very useful in terms of trying to figure out what group structures are possible when you know things about their cardinality. We're going to have to figure out what's a good set for the group to act on. That's going to be non-trivial, but this is going to be one of our keys. And so let's just do the first part over here. The stabilizer is a subgroup of G. So let's prove A. So proof of A. We want to show the stabilizer G sub x is a subgroup. What do we have to do to show that it's a subgroup? We know it lives inside G. What do we have to do to show something's a subgroup? What 4 properties? So if we show it's a group, that's because it lives inside G, that would be enough, right? So what do we have to do? What's the first thing? Closure. So that's actually going to be the hardest one, I think. So let's just dive right in then. So closure. So let's say G1 and G2 are in the stabilizer of X. We must show G1, G2 is in the stabilizer of X. What does it mean for something to be in the stabilizer of X? We have G1 of X equals X, and G2 of X equals X, as G1 and G2 are in the stabilizer. That's the definition of being in the stabilizer. It's what elements of G leave X alone. So G1, G2 of X is equal to G1 of G2 of X by our associativity property. But what is G2 of X? X, because G2 is in the stabilizer. And what's G1 of X? X, because G1 is in the stabilizer. So we proved closure. Which are the 2 easy properties to do? We've got 3 properties left. 2 of them I claim aren't bad. Inverse and identity. Inverse, I think, is a little bit of work. Identity, we know E dotted with X is X, so X has to be in the stabilizer. I'm sorry, so that the identity has to be in the stabilizer. That was one of our properties when we are looking at group actions. The identity axiom was E dotted with X has to be X. So the identity element has to be in the stabilizer. So now we have associativity. What's the word? It's been a long time since I've used this word. Why do we know it's associative? It's inherited, right? We haven't used inheritance in a while. So the last is inverses. If G is in the stabilizer of X, then Gx equals X. So G inverse Gx equals G inverse X, or by associativity, G inverse G of X equals G inverse X, So Ex equals X or X equals X. And G inverse is in the stabilizer. So it's not too bad to just go through the calculation and see that the inverse has to be in. And so we're using crucially the assumed properties of this, group acting on a set. That the identity leaves you alone, and we have associativity. Yes.
Don't you need to prove, I guess, G inverse GX equals to GG inverse X or no?
Okay, which do I have to do?
Just, we don't know if it's commutative, so don't need to prove both sides, or I don't know. It says,
Well, no, we've just shown that G inverse is in the stabilizer,
oh, because it's so, okay.
right?
Okay.
So all we have to do is we just have to show that G inverse is in.
Right.
Yes.
I have a question with the closure part. So
Yes.
with the first line of closure, like what does that mean? You say G1, G2, and G sub X, and then just show that as well?
Well,
G1.
so if G1 and G2 are in the stabilizer, then their product is in the stabilizer. That's what we have to do. It's the product.
I thought that was a problem.
No, sorry. It's G1, G2. This is why I made the comment about bad handwriting. And I will end today with the worst expression to read in mathematics. So the fraction means it's a fraction. The denominator is the capital Greek C. The numerator is the complex conjugate of the capital Greek letter C. So in terms of the worst thing you could ever write, I think, in mathematics. Does anybody know what the absolute value of this quantity would be? You should be able to calculate its absolute value. You have the complex conjugate of C divided by C. It's just 1. So anyways, this is one of the reasons why we try not to use the letter S when we're on the blackboard. And again, some of you are going to be teachers. These are things you want to think about. What do you want to do? Why don't we use the letter S? Looks like a 5. On my general exam, I actually shifted to Roman numerals at one point. All right. This is a good place to stop.